Hi, today we'll be talking about mass moment of inertia. Mass moment of inertia is an important property in the angular motion of objects. Mass moment of inertia is also called the second moment of volume, compared to the first moment of area, where we usually use in finding the center of mass. In determining the mass moment of inertia of complicated objects, there are different properties we can use. So let's start with the definition. This part of topic is on my notes, page 44 to page 45. First of all, if you look at the definition, in this case, we consider a three-dimensional Cartesian coordinate system, x, y, z, following the right-hand rule. The mass moment of inertia with respect to the z-axis is defined and calculated by this equation over here. It equals to the integral of r squared dm, in which r means the perpendicular distance from any directions as long as it is perpendicular to the z-axis. M denotes the mass, dm means the unit mass. If we replace dm with rho dv, here rho means density, capital V means volume, and this calculation can be replaced and written as the integral of r squared times rho times dv. For constant density materials and objects, rho can be taken out of this integral. Therefore, Iz becomes simply r squared dv. The same definition can also be applied to the x and y axis. In those cases, Ix is the integral of r squared times rho times dv, and Iy is the integral of r squared times rho times dv. However, in both cases, r squared must be the square of the distance perpendicular to respective axes. For Ix, the r is measured as shown here. For Iy, the r is measured in this case. Now, another way to look at this integral, which is the mass moment of inertia, is the integral of distance squared over the entire volume. Now, not only that this mass moment of inertia value can be different in different directions, it can also change from point to a point. In other words, the location you choose to calculate and define the xyz for the r squared can be different from point to point. Therefore, by definition, mass moment of inertia is the second moment of volume. If you look at this definition over here, because we're taking the distance square and multiply by the entire volume, therefore this integral will always be positive. Now, let's ask, can this integral be zero? And the answer is yes, as long as the volume becomes zero, or as long as the volume diminishes. Well, that will probably be the lower bound of mass moment of inertia. What about the upper bound? Does mass moment of inertia have an upper bound? And the answer is no. How do we know that? We know that by this, what we call parallel axis theorem. In parallel axis theorem, the distance r can be written as the vector sum of arbitrary values d and the distance from the z-axis to the other two perpendicular axes. In this case, we call x prime and y prime. Now, r squared equals to the sum of squares of d plus x prime squared plus y prime squared. And this integral will lead to three different terms. The first term is just the integral of x prime squared plus y prime squared over the entire volume, or mass. The second term is the integral of x prime over the entire mass times 2d, and the third term is a d squared times the mass integral, which is the total mass. Now, the second term x prime here, because it's integrated over the z-axis, which means that along the z-axis, x prime will have positive values and negative values. When we choose x prime and y prime to be at the center of gravity, this x prime must have symmetric values along the z-axis, which means that the second integral will eventually be 0. Therefore, an arbitrary point, when we choose it to calculate the mass moment of inertia, can be written as the sum of two terms. The first term is what we call the mass moment of inertia at the center of gravity, which is Ig. And the second term will be simply just mass times the distance squared. And the distance will be the distance from the center of gravity to the center point of choice. Now let us see some examples. The first example we'd like to consider here is just a slender bar, or you can consider like a cylindrical object with almost 0 or the minimum diameter. In other words, we will not consider the diameter of the slender bar. We just consider the length, in this case denoted as capital L. To calculate the mass moment of inertia, first thing we have to do is to choose the point. Now let's choose the center, which is, in this case, consider uniform mass density. The center of the mass will be the center of volume, or the center of geometry, which is at the middle point of this slender bar. Let's call this point O. Now when we perform this integral, the mass moment of inertia will be denoted as I0. And this is written as the integral of r squared times dm by definition. Now because we want to integrate this entire slender bar from one end is called I to the other end. And the center of mass is at the middle point, which means that we will have to integrate this along the longitudinal axis. In terms of the values, it's going to be from negative L over 2 to positive L over 2. So for that, we have defined the lower bound and the upper bound. The next thing we have to define is the mass itself. Now how do we do that? Recall the technique we use in calculus. When we want to integrate the entire volume, we have to define the unit volume. In this case, unit volume is denoted by dm. And this dm can be written as the product of mass density times the cross-sectional area times the thickness. And the thickness is denoted by dr. Therefore, density times area times thickness will give us the result as density times the volume, or A times dr is the unit volume dV. Because mass equals density times volume, therefore dm equals to rho times A times dr. And if we do that, we will replace the whole integral dm with rho A times dr. So that's how we're going to do it here. And we put this r squared in this integral, and then we just carry out this integral. And this will lead to this result, which is 1/3 times rho times A times r cubed, from negative L over 2 to positive L over 2. And this will give us the result as 1/12 rho times A times L cubed. So this will be the value for the slender bar at the center of gravity. Now, obviously, we know that if we choose a different point other than the center of gravity, in this case is point O here, both the lower bound and the upper bound will change. Therefore, what about we consider point I? If we consider point I instead of point O and carry out the same integral, this time the lower bound will be 0 and the upper bound will be capital L, because we were going to integrate it from this end, which is 0, to the other end, and which is capital L. And we do the same integral, and the result becomes 1/3 of rho times A times L cubed. Now, how is this value I related to the mass moment of inertia at the center of gravity, in this case is I naught. You can see that if you choose the endpoint of the slender bar and calculate the mass moment of inertia, and it turns out to be the value 4 times greater than the mass moment of inertia at the center of gravity. Let's look at the next example. How about we consider the same place, and the difference between this case and the slender bar case is, in the slender bar case, we only have one dimension, which is longitudinal direction. That is significant. And the perpendicular direction, like we mentioned before, that is the diameter of the slender bar, we consider that insignificant. However, in the case of the same plate, now we want to consider that the perpendicular direction is no longer insignificant. It also has a dimension, we call it h. So in this rectangular thin plate case, we have the length denoted by b and the width denoted by h. The thickness of the thin plate, let's call it regular t here. Now, definition of mass moment of inertia, as we already know it very clearly, is I equals integral of r squared times dm. Therefore, in calculating the mass moment of inertia, the only thing you have to pay attention to is the definition of unit mass. And remember, unit mass always equals to density times unit volume. So the question becomes, how do we determine unit volume? And here, the unit volume is determined by the unit area, which is called dA, times the thickness, and that will give us volume. So dm can be written as rho, which is density, times the thickness, which is constant t, times dA. And dA is nothing but just the unit area on the surface of the thin plate. When we plug all this into this integral, if you're finding the mass moment of inertia with respect to the x-axis, then you have to choose the unit volume not perpendicular to the x-axis but in parallel to the x-axis.